Hello, everyone. My name is Guanqun Yang. Today I'm going to present the ACL 2020 best paper, Beyond Accuracy, Behavior Testing of NLP Model with CheckList. The authors are Marco Tudor-Rebill from Microsoft Research and his co-authors from University of Washington and UC Irvine. This presentation consists of three parts. The first is the introduction of the main contents. In the second part, I will mention some of the limitations of this work. In the last part, I will propose a potential solution for each of the limitations discussed in the second part. So, let's first look at the first main contents of the paper. Every day, we could see the release of hundreds or even thousands of archive papers with exciting titles like XYZ is all you need. This shows the vibrancy of our NLP community, which is good, but it also causes some real problems. For an NLP developer, should he or she adopt particular idea from piles of papers? What his or her decisions should be based upon? Are the nice figures, tables, and metric numbers in bold strong evidence to support these decisions? Probably not. The assumption of using metrics like accuracy, FN score on standard benchmark is that high accuracy is a proxy of good performance. But this is problematic. And this is mainly because of two reasons. First, a single real-value evaluation metric could not actually pinpoint the problems a model face. We may have to look at each of the feeder cases, scratch our heads, and try to figure out what's really going wrong. This is without doubt a long and tedious process. Second, even though we are satisfied with metrics, doing well on the benchmarks is not equivalent to doing well in the wild. Actually, it has been observed that models actually tend to learn shortcuts on standard benchmarks, and this results in an overestimation of performance. So, we need to test NLP models. However, for commercial models, what the developers generally do is looking at error cases and try to create patches in an unsystematic fashion. For research models, there may not even be a debugging process. If a model does not work, many people simply turn their attention to other newer models. Our NLP model is also a piece of software, so maybe it is a good idea to take a step back and recall how we debug regular software. We debug regular software by looking at each of the branches. For example, in this simple program of deciding whether a year is a leap year, there is a bug in line 9. We know the bug is in line 9 with the help of input-output pairs like 2020 true, 2016 true. So the question is, can we extend this idea to debugging NLP models? The answer is yes, but there are some issues. First thing is that there is no branch for an NLP model. An NLP model is like a super complicated black box, and there is no easy way to spell out specific steps an NLP model makes a particular decision. Also, there are more to consider for debugging NLP models. Besides giving steady output for some input, we also need to consider for the following two types. We would like the label to be preserved when label independent part is changed, and we want the model to update the prediction when the label dependent part is changed. To make things more specific, in the first example, we want the sentiment to be same with when Chicago is changed to Dallas and Brazil to Turkey. But when we added the additional sentiment-laden contents like "you're lame" and "I dread you," we should definitely change the sentiment prediction. Facing all the challenges, the idea of this paper is looking at two dimensions. One is the minimal testing unit for NLP model, which is called linguistic capability. Another one is we hope our model to work well. That is, we would like our models to auto-put expected label for a sentence, preserve the prediction when label independent part is changed, and update the prediction when label dependent part is changed. How the authors address the problem in linguistic capability and working well is formulating the problem as a filling the table problem. The rows are different linguistic capabilities, and the columns are different test types. Each of the cells in the table is tabulated with the error rate of a model on generic test cases by the tool developed by the author. In this and next slide, I will expand a little bit on these two dimensions. The first is the linguistic capabilities. Linguistic capabilities correspond to the rows of the error table. The exact number of rows of the table could be different depending on the application. But the author suggests considering negation, SRL, temporal, and vocabulary as a starting point, as shown in this table. For example, the QA no capability, a pair of templates might look as the following, and the only difference is the positive adjective and negative adjective. Because this difference, the expected label for these two templates are different. Another dimension is the test types. The formal definition of these test types are shown here. To put them in perspective, we could take a look at this in this concrete example. For MFT, every time a model outputs a prediction different from expectation, it makes a mistake. Like here, negative comment is wrongly identified positive or neutral, the model fails. For NLP, when the model prediction changes when it is not supposed to, the model makes a mistake. For example, the location should not influence the sentiment, but the model prediction wrongly changes. The model fails. For DIR, when the model does not change in the expected way, the model makes a mistake. For example, when negative sentiment contents are appended, the sentiment should not become more positive but the model actually does. So the model fails. Up to now, we have talked about each design choice of the checklist tool, but we have not seen the pipeline of its application. So let's look at this complete pipeline. We have model M, and we would like to say how capable it is to handle different word choices. The first step is to create specific descriptions under somehow vague linguistic capability, vocab plus pause. Then, the second step is to manually create templates under each of the description. Finally, we generate a lot of test cases by filling slots, and we use the generate test cases to evaluate our model. The authors use the pipeline and find that many of the commercial APIs and research models have severe bugs. For example, for negation, the APIs from Microsoft, Google, and Amazon all have more than 90 and even 100% error rate for some of the linguistic capabilities. Same thing here for the research models. But this is not always the case. Sometimes the models have relatively lower error rate. The similar observation holds for QQP duplicate sentence detection task. For many of the linguistic capabilities, the models fail with close to 100% error rate. This is also the case for diagnosing the question answering system. To show the checklist tool and the pipeline are actually useful for debugging models, the authors conduct two sets of user study. The first set of study involves Microsoft Learning NLP API developers. With the help of the checklist tool, these developers managed to come up with 30 capabilities within 5 hours. Importantly, these capabilities are not considered before, considered but not taken action to address. They are considered addressed but not patched. Overall, many of the failure cases are not known to the community before. In a second set of user study, The authors recruit 18 volunteers with limited NLP experiences and let them use CheckList tool to debug the models. Within less than 2 hours, the group with the help with the CheckList tool managed to find more bugs than the control group that went unaided. Now we go to the second section of this presentation, the limitation of this work. The first limitation of CheckList is that it's now only a semi-automated tool. All the linguistic capabilities, descriptions, and templates had to be manually designed by the developers. If the developer is inexperienced, he or she could let some critical bugs unpatched, and this may lead to severe consequences. The second limitation is that CheckList tool could only review model vulnerabilities but could not patch them. For traditional software, finding bugs often means that we are ready to remove them. But for NLP models, finding bugs does not provide a straightforward way to remove them. We may need to design additional model components to resolve each of the identified vulnerabilities. Then, we go to the third section of this presentation, the potential solutions for each of the limitations. It might be difficult to directly ask machines to come up with high-level linguistic capabilities, description, and templates. But we could diversify and expand existing templates by controlling specific aspects of sentences. Text-style transfer is an area targeted at this problem. Specifically, we aim to learn a representation that could disentangle the property we care about and other information. By controlling the property part of the representation like sentiment, we could generate diverse yet consistent sentences under the same linguistic capabilities. For the second limitation, it turns out that we may not have to go as far as inventing novel model architectures to patch existing vulnerabilities. Previous work has shown that the toxic text classifier shows bias against some identity groups, and the authors managed to reduce the bias with the additional data generated from manual templates. With the help of a CheckList tool, we have already had access to some templates targeted at some specific linguistic capabilities, so they're readily available for us to use them to patch the models in question. Finally, we go to the conclusion section of this presentation. In this presentation, we talk about main contents of the paper, some limitations of this paper, and the potential solutions. For the main contents, the authors operationalize the NLP model debugging as an error table tabulation problem. In this error table, the rows are different linguistic capabilities and the columns are different text types. Through user study, the author showed us that the CheckList tool could indeed help developers find bugs in their model easily. And surprisingly, many of these commercial APIs have severe bugs. For limitations and the potential solutions, we proposed to use text-style transfer to alleviate the dependence on the manual design of templates. Besides, we found it would be straightforward to patch NLP models by directly using generated template sentences.